Okay, so welcome to this little quick review on the four states of matter. This is kind of not really a high school topic, but that's okay. We'll take a second to review it just in case it's something that you're a bit rusty on. So when we talk about the four states of matter, we're really talking about this kind of states. We're not in geography class. And we're talking about the basics, solids, liquids, and gases, those sorts of things. And every one of these images on here shows some of the typical four stages of matter that we're talking about today. So as a way of kind of jumping off on this discussion, I want to talk about the differences between ice and water, and steam for that matter, which we kind of forget is water as well. But at the atomic level, at the chemical level, ice, water, and steam are actually all composed of water molecules. It's a compound. Each water molecule, you can see the picture on the top right corner there, is made up of one oxygen atom and two hydrogen atoms that are bonded together in a stable way. So a single unit of H2O, kind of looks like Mickey Mouse or Pooh Bear over there, is one water molecule. So it's kind of interesting to me that water and ice, and I'll talk about those two, even though they're made of the exact same kinds of atoms and in fact the exact same kind of molecules, they're very different. You definitely don't want to go swimming in a pool of ice, and definitely don't necessarily want to add water to, your soda to make it cold. So what is it about these things that have such different characteristics that we can sort of start to describe the differences between them? So these two differences, where it's the same exact type of molecule, but arranged in some different ways, we call these states of matter. You may also hear it being called a phase of matter as well as the other term. So state of matter, phase of matter means the same thing. In this particular video, I'm going to talk about solid, liquids, and gas at the chemistry level. And I'll briefly mention plasmas at the end, and we'll kind of talk about why we really don't give plasma the love that we should, because it's some awesome stuff. So just to review, in the last video we talked a little bit or showed you some examples of some atomic level diagrams. Well, this is kind of molecular level diagrams, same basic idea. We're going to use circles to represent the different atoms, and again, remember atoms are extremely small, but we're going to use circles to represent the different atoms and the different types of elements. So in this particular diagram, we've got two different elements that are present. There's the blue element and the red element, and you can see they're arranged, they're bonded together in a couple of different ways. We've actually got three different species, and that's actually a real chemistry term, that are present here. We've got some molecules of the red element, and they're all diatomic, so they're A2s, where there's two red circles stuck together. We've got some molecules of the blue element, which is also diatomic like that. And then you can also see mixed in there some molecules of the compound AB, where there's a red circle and a blue circle stuck together. So this particular picture that I've thrown on here is a molecular level diagram of a mixture of a compound and two elements. So there you have it, to review your terms. So what's going on when we're talking about the molecular level diagrams when we're looking at something like water versus ice? So here's a good kind of example, a little bit more sciencey looking, of how we would draw this for water molecules. So you can see there's a picture of what ice kind of looks like at the molecular level, crystal level, and then there's a picture on the bottom right of what water looks like. So each water molecule still has one red oxygen and two little white hydrogens stuck together in those little Pooh Bears. One single water droplet, though, or keep in mind, has just a ridiculously large number of molecules in it. That number there, 3x1021, that means 3 times 10 to the 21st. That's how we say that. We haven't talked about scientific notation, but what you would write that out if you wanted to write that would be a 3 with 21 zeros after it. So just an obnoxiously large number of molecules in a single drop of water. Anyway, so when we're trying to draw a molecular level diagram, obviously we couldn't draw that many, so we just draw a few. So each of those diagrams that's on this picture right here only has, what, maybe 20, if that, molecules that are present, when in reality there's 3 with the 21 zeros after it, molecules that are present in it. So we're really, really oversimplifying when we do these molecular level diagrams. So this one shows the two different states, solid versus liquid. The big key difference here is that even though they have the same number of molecules, the same types of atoms or elements that are present, but the same molecule arrangement, H2O, the difference here is that there's a different distance between those atoms and how they're arranged, or those molecules. And in some cases they're moving further apart, in some cases they're kind of locked together. So we'll get into that a little bit more. So not only when you see these molecular level diagrams do you have to look at kind of what's present, but sort of how close the different molecules are to each other. So this one, we're kind of moving forward this next step. Why is it that ice and water are different? Why do they have different behaviors to them? And again, we have to kind of back up a little bit, some middle school kind of level concepts here. We need to remember that all matter, when you think about a glass of water or an ice cube, is all comprised of trillions of different molecules, but those molecules are always in motion. I'm not saying that the object is moving. I'm saying that even within that object, at the atomic level, those molecules are vibrating or moving around with respect to one another. And we can see proof of it from this very simple example right here. So if you take a drop of food coloring and drop it in a glass of water or two, like there's blue and green in here, that if you just drop them in there and don't stir it, don't touch it, don't swirl it around, those colors will spread around over a while. You may remember this term as being something called diffusion, or if you took a biology class, they would call it osmosis maybe if there was a membrane there. But this movement of these things, this self-mixing behavior, is directly related to the fact that those little molecules inside the water are actually moving around. So as the water molecules bump into the food coloring molecules, it kind of knocks them out of place a little bit. And then over time, they're going to spread throughout that entire glass of water. And then they're going to mix together eventually, and we'll see that kind of green color. So kind of continuing on further, let's take a look at this again. This is called the kinetic molecular theory of motion. This molecular motion theory is that molecules are always in motion, always, always, always. Even if you can't see it at your level, at their level, there's actually quite a little bit of jostling and wiggling going around. So as we put something in there like a crystal or say a sugar cube or a drop of food coloring, that those water molecules are going to start to bounce into one another. And you'll see those terms solute and solvent in there. We'll get into those a little bit more again soon, but that dye molecule is bouncing around inside the solution or the solvent of the water. And then over time, they're going to mix together. At the third picture, the one that's on the right, you can see that over time, that self-mixing will occur, and that after quite a while, it will be completely stirred up. We don't have to do anything to it. Those water molecules and the dye molecules are sort of thoroughly mixed together. Now, how does this have to do with ice cubes? Okay, well, let's link this back. It turns out there's a next step, that this concept of molecular motion is not just related to the things that are present, but also to the temperature of the things that are there. And temperature actually is a measure of how quickly those molecules are moving. It's a measure of energy, a type of kinetic energy, which again seems kind of bizarre to us to think about just taking something's temperature. Well, here we can kind of see evidence of this. So you've got two different beakers on this picture right here. The purple one is quite a bit warmer. The blue one on the right is quite a bit colder. And so with these two pictures, the drop of food coloring was added at the same time, and the picture was taken pretty much a few minutes later. That purple one has mixed, self-mixed a lot faster. The blue one is mixing, but quite a bit slower, and it's all due to the motion of the molecules. Those molecules in the purple one are just banging around against one another really, really fast, and so it's causing that self-mixing to occur quickly. In that cold one, they're just sort of moving just kind of really slowly. They're in there and they're moving around, but not fast enough to cause the same rate of stirring that we would see in that one on the left. So again, diffusion rate or that mixing style depends on temperature, and that temperature is related to the motion of the molecules inside the matter that we're looking at. So this relates directly to this idea of states of matter. States of matter are all about temperature, and by temperature, they're all about molecular motion. A solid and a liquid and a gas of the same material is simply a difference in molecular motion of the molecules within that particular matter. So if you had something that it was frozen, those molecules are moving really, really slowly. If you had to try to do this, I can't even imagine doing this, but if you did it with steam, something that was a gas, those molecules are moving really, really quickly. So again, it's that idea of the phases or the states of matter is simply a matter of relative motion. Are they so cold that they're basically holding still, or so hot that they're bouncing off the walls and going crazy in terms of what they are? So here's what it looks like if we want to do like a molecular level diagram. Temperature is related to energy and molecular motion. So if you go from a solid to a liquid to a gas, you're increasing temperature, which means you're increasing energy. And as the solids have the least amount of molecular motion, those molecules are barely moving, they can kind of snuggle in together and they pack up close, and we call that a crystal or a solid. When they're in a liquid form, there's a little bit more motion on there, and they kind of are slippery. They sort of slide past one another, like we think about a liquid flowing. And if it's a gas, they're really moving like crazy, and they're so energetic that they're actually separated from one another now with space. And again, we call that a gas. So here's kind of another way to sort of interpret that. What are the changes in phase or the changes in state? We go from a solid to a liquid to a gas. So these terms that are on here are actually quite important. The idea of their shape and then their volume is something that you will be asked in terms of describing a solid, liquid, and gas. So we would say a solid is rigid. In other words, it holds its shape. And that's what the term fixed means. A fixed shape means it's not going to sit there and just fall apart. Has a fixed volume as well. It means you can't really compress it. You can't make it smaller. And I'm talking about true solids here. I'm not talking about something like foam that actually has a gas that's trapped inside of it, so don't get tricky on me. If you're talking about a liquid kind of moving up, that increased molecular motion means it's no longer rigid. You know that liquids aren't rigid, that it kind of flows all over the place, and that's that step down where it says no fixed shape. Again, you take a liquid out of its container, it's going to go splash all over the place. It doesn't hold its shape. Fixed volume is kind of an interesting one. You can't compress a liquid. When you have 10 milliliters of water, or a gallon of water, if you want to think about it that way, you can't make it any smaller than that. You can't squish water into a smaller container. A lot of people don't realize that's true, so try it sometime. You'll see that it doesn't work. And then gases, the characteristic of those. So those molecules are so far apart now that they're definitely not rigid. They're bouncing all over the place, no fixed shape. But they also don't have a fixed volume because those molecules are so far apart that you can kind of compress them and take the space out between the atoms. So gases are the only ones that are truly not a fixed volume. So a little bit different. So make sure that you check into those terms a bit. Here's some examples in terms of just kind of what they look like. You're most familiar with solids because they're the ones that we can see and touch. Most elements, especially metals, are going to be solid at room temperature. There's only a couple that are liquid. You may have seen liquid mercury before in an old thermometer or something like that. That's very toxic, so don't touch it if you see it. The nonmetals, though, some of those can be gases. And so you've heard of hydrogen gas, helium gas, like in balloons, oxygen gas that we breathe, nitrogen. Those things are gases. Those molecules are really far apart. Just at room temperature, they sort of already turn to a gas at that stage. But any element can go through any phase. Any compound can as well. Well, not quite. Sometimes they set on fire instead, so don't listen to that. But we can take a solid and melt it, and we can even melt it and then turn it into a gas, which is kind of crazy to think about melted iron and then talk about it as a vapor. Pretty wild. Water's the only one that we typically see all three phases at our kind of room temperature that won't really kill us. So here's some weird ones just so you can kind of see some examples. That one on the top left, if you've ever seen someone do YouTube it, experiments with liquid nitrogen where they freeze something and then shatter it. So there's a rose that's been dipped in liquid nitrogen and then it's being just blown apart basically as it's being kind of vaporized. If you've ever heard of carbon dioxide is dry ice. And so you may have heard of it under that name. So that's what's in that spoon right there. Carbon dioxide is usually a gas. You breathe it out. If you make it cold enough, it does turn into a solid that we call dry ice. And dry ice is called dry ice because it doesn't really melt very well. It doesn't like to go to liquid. It likes to turn immediately to a vapor, to a gas. So you don't typically see carbon dioxide as a liquid very often. And then over on the bottom left, you can see iron, molten iron. So iron is a liquid phase. And yeah, you could heat it up and get it up to a gas if you want to. It'd be ridiculously hot. So just as a quick reminder, when we say something is frozen, it's kind of difficult to get away from that idea. It doesn't mean that it's cold. It actually means it's a solid. So if we talk about liquid nitrogen, yes, it's cold, but we can talk about iron as being frozen at room temperature. It's already a solid. Same thing, the term melted doesn't necessarily mean that it's hot. It simply means that it's warmer than it was when it was a solid, and it typically means that it's a liquid. So certain things are already melted at room temperature, and certain things kind of going along are actually boiled or vaporized at room temperature, like gases like oxygen and nitrogen. Again, doesn't mean they're hot. It just is referring to the phase change, the change of state that they're in. So the last one, I'll let you read the words over in that diagram there. There's lots of words. But here's some good examples of molecular level drawings, again, of a solid, a liquid, a gas. Take a close look at how those atoms are packed together or not packed together as we get up to a gas. And then you see that one on the right, which is called a plasma. Plasmas are like a gas on steroids. They're not just hot, but they're so hot that literally the atoms are starting to come apart. The electrons are no longer with the nuclei that made them up, so the atoms are breaking down a bit. And that takes an incredible amount of energy to make that happen. So it's not something that we see in a chemistry lab, although we do see examples of it on Earth here quite often. It turns out that if you've ever seen lightning before, you have seen a plasma. That's actually what sparks are as well, where it's actually so high energy that for just a short instant, you do see that sort of separated ionized gas. I don't like calling it an ionized gas because it's not really a gas. But inside fluorescent light bulbs, you also see plasmas. Those cool, glow balls that you touch and they all look all like lightning. That's a plasma. Plasma TVs, obviously, hence that's the name. But it turns out that actually plasmas are incredibly common. The sun and all stars are made of plasma. So it's the most common form of matter in the universe, just not real common here on Earth. Because if you know anyone that's ever, been struck by lightning, it tends to not react really well with the other kinds of matter. It doesn't work and play well with others. So when you come into contact with something that's high in energy, it tends to cause damage, I think is the word for that. So anyway, if you've ever played with fire before, you're playing with like the lowest energy version of plasma. And even that is dangerous with a real short amount of exposure. So that's why we don't talk about it that much in chemistry. So here you go, your 4 states of matter, what you should be able to do as a result of today. So you should be able to define what a state of matter or a phase of matter is and list all 4. And then you should be able to give some understanding about how all matter is made up of molecules in motion, and then kind of relate that to some different concepts that we've seen in here, like temperature and rates of diffusion, how quickly things mix based upon the fact that those things are made of moving molecules all the time. And then kind of the key one here is to make sure that you understand that there's a relationship between the states of matter, solid, liquid, and gas, and the changes in molecular motion, that solids have the least molecular motion, gases have the most molecular motion, liquids are in between, and then again, plasmas are kind of weird. And then you should be able to define solids, liquid, and gases in terms of molecular packing, like how close the atoms are, whether they have a fixed volume or a variable volume, whether they flow, and whether they can be compressed or not, and then whether or not they have a fixed shape. So those kinds of definitions. And then if I show you a picture of it, of just those circles, whether they're close together or far apart, you should be able to tell me if that's a solid, liquid, or a gas. And then again, finally, if you want to go a little bit further, you can describe some things about plasmas and kind of explain how they're unique, different than the other 4 states, and kind of talk about why we don't really discuss them that much in chemistry, even though they're ridiculously cool. So thanks. I hope you enjoyed it. See you next time.